calculate a removable discounted?
Oh, well, here's a removable discontinuity.
Okay, there you go.
So at x equals -1, what if this is really x minus 1? So its graph looks like this, but at -1 there's a hole, right? That's a removable discontinuity. That's certainly not a giant jump. Now this one has an asymptote at 1, right? Functions can be pretty bad.
Okay.
You guys missed it. This is an interesting thing. If you have a function like this,
Step function.
yeah, but this is a specific kind that we're going to need when we start to study the Stieltjes in it. When we did our overview, we talked about this. Do you remember? It's a Cadlag function. And that's a French abbreviation. Continuous from the right, limited from the left. So if I come at it this way, it's continuous, right? But if I come at it this way, all my limits exist. I run, this is sort of a barrage dead end here, right?
One-sided loop exists, but it's not.
Yes, it's not continuous. That's called a Cadlag function in the literature. I think the anglicized thing is right continuous, left limited. They call them RCL functions too. At any rate, okay, we know what a continuous function is. What's uniformly continuous?
X and Y, but that's the value of X.
Okay, you're very, very close, very close.
Well, continuous, your epsilon x.
For pre-assigned epsilon greater than 0, there exists a delta, which is a function only of epsilon, not of continuous, right? Delta is only dependent on epsilon, such that if the absolute separation of 2 points x and y is less than that, that implies that the absolute variation of the function at those 2 points is less than epsilon. Whenever that happens, you say that the function f is uniformly continuous on the domain that contains the x's and y's here. So a constant function, for example, is trivially uniformly continuous on the entire real number line, right? How about the function f of x equals x? Is the domain of uniform continuity there, the entire real line? Well, what do you have to do? If I give you an epsilon, you have to find a delta so that if you keep 2 points within delta, the function values on those points correspond to a distance less than epsilon. Can I do that? What if you just set delta equal to epsilon? Would that do it? No. This is the picture. This is the picture. This is the function. So if I insist that 2 points be no further apart than delta, right? What's the vertical separation going to be at most? Epsilon, right? So keep within delta on the x-axis, and on the y-axis the images will be within epsilon, and that shows that that function is uniformly continuous. All right. Well, does that mean every continuous function is uniformly continuous? Consider f of x equals 1 over x on our famous set here. Is that uniformly continuous or not? If not, why not? Give me a counter. You say no, so your intuition is right. Let's prove that. Does anybody think it is uniformly continuous? Well, is it continuous?
Yes.
You're sure about that? It's continuous. So you go pick a point, and the limit comes at it from either side, and the function's certainly well defined there. Zero's out of the picture. So you go find a point, and you're good there on the definition of the function. The limits for both sides are the same and equal to value function there. So apparently it's continuous on that interval, but it's not uniformly continuous. Why?
Because the limit approaching zero for the right definition. Give me any.
Well, let's appeal. Okay, that's halfway there. Appeal to the definition. Here, I'm going to give you an epsilon, and then we'll propose a delta and show that no delta works. That's what we have to do, right?
Yeah.
Fix epsilon and show that no delta really works. So give it epsilon greater than 0. All right. Suppose 1 over x minus 1 over y, that's supposed to be less than epsilon if x minus y is less than some proposed delta. Right, that's what's supposed to happen. That's what we think. Well, that's what we'd like to happen. If that happens, it's uniformly continuous. I don't think we can make this occur. Why? Okay. So if I make this really, really small, if that is all there was, we'd be in good shape. But look, it doesn't matter how small this is. If you move these guys over towards 0, this is really, 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 really small, right? 1 over something that's extremely small will pump this thing up. Pump it up so that this thing can exceed epsilon, right? So what we're trying to show is that if this is epsilon and it's supposed to be greater than 1 over x minus 1 over y is 1 over absolute xy, absolute x minus y, and this is equal to delta. Here's our relationship. We have epsilon is greater than absolute x minus y over delta. Sorry, the other way around. Delta over absolute xy. Okay? And this has to be true for all xy. Well, multiply through by absolute xy. Given this, if you specify this, I'll just move. I'll push x and y so damn close to 0 that it will pare this epsilon down and it will no longer be greater than delta. I will defeat you if you try to. I give you the epsilon, you give me the delta, and I go back and say, oh no, xy is really, really small. Small enough to make the product of xy and epsilon actually less than the delta that you give me. I can defeat every delta that you give me, right? Do you see why then it's not uniformly continuous? Continuous, but not uniformly so. Why are we interested in this? This is why. When you do an integral from A to B, say, sorry. Okay. What I would like to do is have a partition. And then I don't want the error of my rectangular approximation to be too big. In fact, I would like the max error for every elemental rectangle pair to be less than epsilon vertically, right? And then it'll be times the width down here. If I can do that, if uniformly these two things are all within epsilon, top and bottom, right? then the whole approximation is going to be within epsilon times b minus a, right? If I come in under and come in over each time, the difference between the overestimate and the underestimate is never going to be greater than this. If I can control the individual errors by the epsilon.
By making it smaller,
Yeah.
smaller, making the error smaller, smaller.
Right. But can I do this? Can I say I would like the mesh of the partition to be no greater than delta? Is that going to force all of these to be less than epsilon? Well, we just saw that doesn't work so good unless what?
Yeah.
It has to be uniformly continuous. This is where Cauchy pumped it. Yes?
Is this where the notion of uniform continuity comes from?
It was invented, I think, by Weierstrass to address this exact problem.